Today we will be studying about magnetic effects of current. The first topic we will be studying about is Biot-Savart's law. Now Biot-Savart's law tells you how to find magnetic field due to a current element, and then we'll try to find how to get its direction. Now consider a current carrying wire. So this is a wire which carries a current, say I. I will take a small element, say an element of length dl, and due to this current element, say we have to find field at a point P such that this P point is at a distance r from your element. Say theta is the angle between your current element and your position vector. Now according to Biot-Savart's, the field produced by this small element, say dB, is directly proportional to the current flowing through it, is directly proportional to the length of the element, it is directly proportional to sine theta, and it is inversely proportional to the square of the distance between them. Now if you combine this, you will have dB is equal to some constant mu naught upon 4 pi I dl sine theta upon r square. Now this formula gives you the strength of the field produced by a small element, current element IDL at a point P. Now if you need to find the direction of this field, then you have to use right hand thumb rule. Now consider you are given a conductor which carries, say, a current I, and say you need to find what is the field at this point P. Now in order to find the field, you will be using this formula to get the magnitude of the field. In order to find the direction, we will be using the right hand thumb rule. Now we will be holding the conductor in such a way that your thumb is pointing along the direction of the current. Then the curl of the fingers, that means the way your fingers are being bent, that gives you the direction of magnetic field lines. So if I hold the conductor in my hand, my curl of the fingers is like this. That means along this path I will have my magnetic field lines. Now if I want to find the field produced at this point P, so I need to just draw a tangent at this point. Or in other words, if you look carefully, the magnetic field's direction at this point P will be inward. Now an inward field is always represented by cross. Similarly, suppose my P point lies on this point. So if I want to find the direction of the magnetic field at this point, I will be just drawing a tangent at this point which will be acting outward. Now an outward field is always represented by dot. So using right hand thumb rule, you will get the direction, and using this Biot-Savart's law, you will get the magnitude. Now always remember, one of the easiest ways of finding the direction of the magnetic field, which generally I use, is suppose this is the direction in which the current flows, and say you want to find field at this point. Now what you need to do very simply is, you have to keep your right hand like this. The thumb should be pointing in the direction in which the current is flowing. All the four fingers should be pointing in that direction where you need to find the field. Now look at the direction in which the palm is facing. Your palm is facing inward. That means field will be acting inward. We'll try once again. Say the point is lying at this side. Now hold your hand now like this. Current is flowing in the upward direction. You want to find the field at this point. Look at the palm. Your palm is facing outward. So in this direction, you will have the direction of the magnetic field. Now this rule you can apply anywhere to find the direction of magnetic field. Now we'll study the application of Biot-Savart's law. Magnetic field at the center of a current carrying circular loop. Suppose you're given a circular loop, a current carrying circular loop, say I current is flowing through it. Radius of this circular loop is say R. Now in order to apply the Biot-Savart's law, we'll consider a small element over here, say dl is the length of the element. We need to find field at this point, say at O. According to Biot-Savart's law, the field produced due to this small element will be equal to mu naught upon 4 pi I into length of the element, that is dl, into sine theta. Remember, theta was the angle between the current element and your position vector. Now this is the direction in which your current element acts. Now this is the direction of your position vector. So this angle will be 90 degree. So this can be written as sine 90 divided by square of the distance, that is r square. So if I need to find the net magnetic field, I'll integrate both sides. If I integrate, I'll get B is equal to mu naught upon 4 pi I into. If I integrate dl, I'll get the total length, that is a circumference, that is 2 pi r divided by r square. So you'll have B is equal to mu naught I upon 2r. So this will be the strength of your magnetic field at the center of a current carrying circular loop. Now look at the direction. If I take this small element, if you are using right hand thumb rule, check the current is flowing in this direction. So hold your hand like this. The curl of the fingers gives you a direction of field lines. So field lines are moving like this. That means field will be acting inward. Or the easiest technique which I gave you is, current is flowing in this direction. You need to find the field at this point. Hold your right hand like this. Your thumb is pointing along the direction in which the current is flowing. All the 4 fingers are along the direction where you want to find the field. Now look at the palm. Your palm is facing inward. Your palm is facing inward means the field is acting inward. Or only for circular loop, there is one more technique. What you can do is, the direction in which the current flows, you keep the curl of the fingers. Then thumb will give direction of magnetic field. The current is flowing clockwise, so hold your hand like this. So this gives the direction of current. Now look at the thumb. Thumb is acting, pointing inwards, or in other words, field will be acting inward. Now you may have cases where you find that you may not be given a circular loop. Suppose you are given a simple arc. Say you are given an arc like this. Say this arc subtends an angle alpha and it is carrying a current, say I. Again I will be taking a small element. Let me take an element dl. So field produced by this small element will be dB is equal to mu naught upon 4 pi I dl sine 90 upon r square. For any circular element, do remember the angle between the current element and your position vector will be always 90 degree. Now in order to find the total magnetic field, I'll integrate both sides. Now on integrating, I'll get dB is equal to mu naught upon 4 pi I into. If I integrate dl, I'll get length of the entire element. Now length of the entire element in terms of the angle subtended alpha will be r into alpha divided by r square. Or you will have B is equal to mu naught upon 4 pi I alpha upon r. Again you can check the direction of the field. The current is flowing in this direction, so field will be acting inward. So this formula gives you the magnetic field due to a circular arc, whereas this gives you the magnetic field due to a complete circular loop at its center. Now we will find magnetic field along the axial line of a current carrying loop. Now let's consider a current carrying circular loop. So this is a current carrying circular loop of say radius r, and we need to find the field at this point say P, which is at a distance a from the center. Say a current I flows through this. Now do remember, I place the coil like this. So this is your invert part. This is placed perpendicular to the plane and the current is flowing in this fashion. Now in order to apply Biot-Savart's law, I will take a small element dl and I need to find field at this point P. Now according to Biot-Savart's law, the field produced dB will be equal to mu naught upon 4 pi I dl sine 90 divided by root of r square plus a squares whole square. Now this will be the field produced at this point. Now if you look carefully at this particular element, the current will be flowing outward like this and you need to find field at this point. So hold your hand like this, current is flowing in this direction, you need to find field at P point. So hold your hand like this, you will find that your field will be acting in this direction, or in other words, normal to the opposition vector, in this direction you will have vector dB. Now if I take this angle to be say phi, then this angle also will be phi. Now if I resolve dB into two components, along this direction I have dB cos phi and along this direction I have dB sin phi. Now exactly diametrically opposite, if I take a small element over here, say of again of length dl, you will find that the magnitude of the field remains same, but you will find that the direction just reverses. Because at this particular element you will find that the current is flowing inward, here the current was flowing outward, here the current is flowing inward. So I will keep my hand like this, I need to find field at this point, current is flowing inward. My palm, if you look, it is facing along this side, or in other words, I will have field along this direction. This will be dB. Now if this angle is phi, since I have taken diametrically opposite element I have taken, so again this angle will be phi, this angle also will be phi. Now if I resolve dB again into two components, I will have one dB cos phi and along this direction I will again have dB sin phi. So both these dB cos phi components, they will get cancel off. My net magnetic field B will be equal to integral of dB sin phi, or B will be equal to integral of, if I substitute the value of dB, I will have mu naught upon 4 pi I dl sin 90 divided by r square plus a square into sin phi. Now from the figure, your sin phi is r divided by root of r square plus a square, or B will be equal to mu naught upon 4 pi I into, if I integrate dl, I will get 2 pi r into r divided by r square plus a square raised to power 3 by 2, or B will be equal to mu naught upon 4 pi I 2I into pi r square divided by r square plus a square raised to power 3 by 2. Now this gives me the strength of the magnetic field. Now if you look at the figure, you can see that the direction of the magnetic field is normal to the plane of a circular coil and it is acting along towards right. This is the direction of the magnetic field. Now we can rewrite this. If you just look it carefully, on the numerator side I have I into pi r square. Now pi r square is what? The area. So this can be rewritten as B is equal to mu naught upon 4 pi twice I divided by r square plus a square raised to power 3 by 2. Now here you will have pi r square is your area. Now remember, number of turns into current into area, this will give you the magnetic moment. N into I into A gives you magnetic moment. Now since we have only one turn, N will be equal to 1. So magnetic moment will be equal to I into A, or B can be written as B is equal to mu naught twice M divided by 4 pi r square plus a square raised to power 3 by 2. In other words, every current carrying circular loop will behave as a magnet, and this magnet will have a magnetic moment M equal to NIA, or you can even say the current carrying circular loop will be acting as a magnetic dipole having magnetic moment M is equal to NIA. Now remember, the direction of magnetic moment is always from south pole towards north pole. Now how to check which side is the south pole and which side is the north pole? What you need to do is just look in which way the current is actually flowing. Now if you find that the current is flowing along the clockwise direction, then that end will behave as a south pole. And if you find the current is flowing in the anti-clockwise direction, then that end will behave as a north pole. Now if you look at this side, the current is flowing in this direction, or in other words, if you face towards the loop from this side, the current is flowing in the clockwise direction, or in other words, this side which is facing toward me will be acting as a south pole. Obviously the other side will be acting as a north pole, and the direction of the magnetic field will be from south to north, or in other words, in this direction your magnetic moment will be acting, and along the same direction you find that your field is also acting. Next we will be studying magnetic field due to a straight current carrying wire. Magnetic field due to a straight current carrying wire. Now consider this. You are given a straight wire which carries a current, say I. We need to find what is the field at this point, say at a distance A. A is your perpendicular distance, and P is the point where we need to find the magnetic field. I will take a small element, say an element of length dl. This distance is say L. I'll join the element with P. Say this distance is R, and this angle let me consider to be theta, and this angle let me consider it to be phi. Now remember, phi is a variable. If I join the two extreme ends towards P, this entire angle is say phi 1, and this angle is say phi 2. Now if I apply Biot-Savart's law, the field due to this small element dB will be equal to mu naught upon 4 pi I into dl into sine theta divided by r square. Now the field will be acting inward as per rule. The current is flowing in the upward direction. You need to find field at this point. If you look at the figure, you can find the field is acting inward. But the problem is we cannot integrate it directly, because you can see that there are more than one variables. So what we do is we'll try to convert these variables in terms of a single variable, say in terms of an angle phi. Now if you look at the figure, theta plus phi is equal to 90 degree. Theta plus phi plus 90 is 180. So theta plus phi will be equal to 90 degree, or I can write theta will be equal to 90 minus phi. Now from the expression, Sine theta can be rewritten as sine 90 minus phi is equal to cos phi. Similarly, if you look at the figure, we'll find the value of tan phi from the triangle. Tan phi will be equal to perpendicular upon base. Your perpendicular is L, your base is A. So L will be equal to A into tan phi. If I differentiate both sides, I have dl is equal to A into differential of tan phi is sec square phi d phi. So instead of dl, I can substitute this in terms of phi because A is constant. Instead of sine theta, I can rewrite this as cos phi. Similarly, if you look at the figure, cos phi will be equal to base upon hypotenuse. Base is A, hypotenuse is R. So here R will become equal to A divided by cos phi, that is equal to A sec phi. So I have all the variables converted in terms of phi. Now I'll substitute instead of cos theta, sine theta, I'll substitute cos phi. Instead of dl, I'll substitute this. Instead of r, I'll substitute this. So if I substitute this, I will have dB is equal to mu naught upon 4 pi I into dl. So instead of dl, I can write a sec square phi d phi divided by r square. So instead of r square, I can write a square sec square phi. Then I have sine theta. Instead of sine theta, I can write cos phi. So we write d by dB will be equal to mu naught upon 4 pi I sec square phi get cancelled. A and A get cancelled. So I will have I by A into cos phi d phi. Now if you look carefully at the expression, mu naught upon 4 pi I is a constant, A is a perpendicular distance, that is also a constant. Your only single variable is phi. Now if you look at the figure, phi varies from minus phi 1 to plus phi 2. So if I integrate, I'll put the limit as minus phi 1 to plus phi 2. Now if you integrate and substitute the limits, you will have b equal to mu naught upon 4 pi I by A sine phi 1 plus sine phi 2. Now this will be the field due to a straight current carrying wire. Now we'll consider a special case. Suppose this wire is infinitely long. Now if this wire's length if you increase, if you look at the figure carefully, suppose I made the length of the wire to be this much. Then look at the angle phi 1. You find that your phi 1 will increase. Now it will become this much. Similarly, if I increase the length toward this side, you will find that your phi 2 again increases. Or in other words, if the length of the wire becomes infinite, then phi 1 will become equal to 90 degree. Phi 2 will also become 90 degree. Or the net magnetic field B can be written as mu naught upon 4 pi I by A sine 90 plus sine 90. Sine 90 is 1, so it becomes 2. So we will have the strength of the magnetic field as mu naught upon 4 pi 2I by A. Now we'll see few questions from the module. Find the magnetic field at the center O of the given circular loop. Now you are given a circular loop. We need to find what is the field at the point O. The loop is connected to a source of EMF E. Now let me assume that radius of the circular loop is say R. A current I is flowing into the loop. At this point A, the current branches out into 2. Now let me assume I1 is the current flowing through the upper circular arc Similarly, I2 is the current flowing through the lower circular arc. Say the upper circular arc has a length L1. So this is L1. Similarly, the inner loop has a length, say, L2. Now, if you use Biot-Savart's law, the field produced, say, B1 due to the upper part can be written as mu naught upon 4 pi I1 into length of the loop, that is L1, divided by R square. Now this field will be acting in the inward direction, so it is cross. Similarly, if I find field due to the second arc, that is a lower arc whose length is L2 and which carries a current I2, can be written as mu naught upon 4 pi I2 into L2 divided by R square. The current is flowing along this direction, so the field will be acting outward, so this direction can be represented by dot. Now if you look carefully, both the fields direction are acting in the opposite direction. Now what we'll do is we'll check the relation between the two currents, I1 and I2. Now the upper part will have some resistance, the lower part will also have some resistance. Now if you look carefully, both the wires, the upper one and the lower one, are connected across AB. So I can assume that I have two resistors and these two resistors are connected in parallel. Now if they are connected in parallel, then the potential difference will remain same. So I can write I1 into R1 is equal to I2 into R2, where R1 is the resistance of the upper part, R2 is the resistance of the lower part. Or I can rewrite this as I1 into, instead of R1, I can write rho L1 upon A is equal to I2 into rho L2 by A. Now since the entire loop is made up of same material, your resistivity will remain same, area of cross section also remains same, but your length is varying, that's why the resistance is varying. Now from this you get I1 L1 is equal to I2 L2. Now if you look at the expression of B1 and B2, you have expression mu naught upon 4 pi R square common in both, and you find that there is a term I1 L1 and here there is a term I2 L2, and yet prove that since they are connected in parallel, I1 L1 will be equal to I2 L2. This means that B1 in magnitude will be equal to B2. At the same time, we have already proved that the directions are opposite. Now since B1 and B2 in magnitude are equal and the directions are opposite, it means that your net field at the center will be always 0. Now do remember, in cases like this, wherever you connect A and B, whether diametrical opposite or any way you connect, or you connect like this, you will always find that your net field at the center will be always 0. We will be doing one more question from the module. A current flows along a thin wire shaped as a regular polygon of n sides, which can be inscribed into a circle of radius capital R. Find the magnetic field at the center of the polygon. ये आपको एक पॉलीगन दे रखा है, से ऑफ n साइड्स, इसको आपने सर्कल के अंदर इंस्क्राइब किया हुआ. अगर आपने सर्कल के अंदर इंस्क्राइब किया हुआ तो दिस डिस्टेंस विल बी r, द रेडियस ऑफ दैट सर्कल. हम क्या करेंगे, किसी भी एक साइड की वजह से सेंटर पे फील्ड निकाल लेंगे और आप ये देखोगे कि हर एलिमेंट की वजह से फील्ड की डायरेक्शन एक ही होगी. तो इसलिए जस्ट यू हैव टू ऐड और मल्टीप्लाई बाय n, यू विल गेट द नेट फील्ड. ना पहले आप डायरेक्शन देखिए, द करंट इज फ्लोइंग अलोंग दिस साइड, फील्ड आपको यहाँ निकालना है, हाथ आप ऐसे रखिए, thumb is giving the direction of current, all the four fingers are pointing towards the point where you need to find the field, your palm is facing inward, so your magnetic field will be acting inward. Now I'll take one part, I'll take only this side. Now this is a straight conductor. You know, magnetic field due to a straight conductor is given by mu naught upon 4 pi I divided by A, and A was the perpendicular distance. Now for me in the figure, this is the perpendicular distance. Now this side I have taken R, this angle is theta, so this becomes r cos theta. So it will be r cos theta into sine. In the formula it was sine phi 1 plus phi 2. Now here you can see the angle subtended are theta and theta. So I'll write it as what? Sine theta plus sine theta, that is 2 sine theta. Now this is a field produced by one element. Now like this you have how many? You have n. So total field at the center can be written as n times the field produced by one segment. Or in other words, the field produced B will be equal to n into mu naught upon 4 pi I into 2 divided by r into tan theta. Now from the figure, if you look at theta, you will find that the entire angle subtended at the center is 2 pi. If you have a polygon of n side, then each side will subtend an angle of 2 pi divided by n. Now half of this is basically theta, or in other words, from the figure, theta will be equal to half of this angle, that will be pi by n. Remember, 2 pi by n is the angle subtended by one segment, so theta will be equal to pi by n. So we can replace this as b is equal to n into mu naught upon 4 pi twice I upon r into, instead of tan theta, this one you can write tan pi by n. Now this is a field produced at the center. Now if I just prolong a bit more on this, suppose n tends to infinity. If n tends to infinity, then this angle becomes very small. In mathematics you have studied, when the angle is small, tan theta can be replaced by theta. So I can rewrite the expression as b is equal to n times mu naught upon 4 pi 2I upon r. Since we are replacing tan theta by theta, I can write this as pi by n. Your n and n will get cancelled. Pi get cancels, 2, 4 get cancelled. You'll have b is equal to mu naught I by 2r. Now if you remember, this is a field produced at the center of a circular loop. Or in other words, if n tends to infinity for a regular polygon, you'll find that you will get a circular loop and whose field at the center can be given as mu naught I by 2r. And since the current is flowing in the clockwise direction, your field will be acting inward. So this will be the net field. आगे हम पढ़ेंगे एम्पियर्स सर्क्यूटल लॉ. एम्पियर्स सर्क्यूटल लॉ एक ऐसा पावरफुल टूल है जिससे हम मैग्नेटिक फील्ड निकाल सकते हैं, जिस तरीके से हमने गॉस थ्योरम से इलेक्ट्रिक फील्ड निकाला था. एम्पियर्स सर्क्यूटल लॉ स्टेट्स दैट द लाइन इंटीग्रल ऑफ मैग्नेटिक फील्ड ओवर अ क्लोज पाथ इज इक्वल टू म्यू नॉट टाइम्स द करंट थ्रेडिंग थ्रू दैट पाथ. मैथमेटिकली अगर लिखें तो आप ऐसे लिख सकते हो, इंटीग्रल b डॉट dl इज इक्वल टू म्यू नॉट टाइम्स आई. जैसे आप गॉस थ्योरम में एक इमेजिनरी सरफेस लेते थे, वैसे ही यहाँ पे जब एम्पियर सर्किट लॉ में अप्लाई करेंगे तो विल बी टेकिंग a closed loop, and remember that closed loop is an imaginary path. इसको प्रूव करने के लिए we'll consider a straight conductor, infinitely long straight conductor, जिसमें से मान लीजिए I करंट फ्लो कर रहा है. अब एक एम्पीरियन लूप लीजिए, मान लीजिए ये मेरा एक एम्पीरियन लूप है ऑफ रेडियस से r. इस पॉइंट पे मान लीजिए मुझे ये जो पॉइंट है इस पे मुझे फील्ड पता ऑलरेडी, क्योंकि ये इन्फाइनेटली लॉन्ग वायर है, तो इस पॉइंट पे मुझे फील्ड पता ऑलरेडी. इस फील्ड की डायरेक्शन किधर होगी? अगर करंट ऊपर फ्लो कर रहा है तो फील्ड की डायरेक्शन इनवर्ट होगी. विल स्टार्ट विद द लेफ्ट हैंड साइड. इंटीग्रल b डॉट dl विल बी इक्वल टू, यहाँ पे अगर मैं एक छोटा सा एलिमेंट लूँ तो dl वेक्टर dl की डायरेक्शन इनवर्ड होगी, जो फील्ड की डायरेक्शन होगी वो भी इनवर्ड होगी. तो इसको मैं लिख सकता हूँ इंटीग्रल b इंटू डी, और दैट इज इक्वल टू, b को मैं बाहर निकाल लेता हूँ, b इंटू इंटीग्रल ऑफ dl. इन्फिनिटली लॉन्ग वायर के वजह से फील्ड का फॉर्मूला क्या होता है? म्यू नॉट अपॉन 4 पाई 2i बाई r. ये तो आपका फील्ड हो गया. डीएल को अगर मैं इंटीग्रेट करूं तो मुझे क्या मिलेगा, सरकमफ्रेंस मिलेगा, वो कितना होगा 2 पाई आर। तो अगर आप यहां से देखें तो आपको क्या मिलता है, म्यू नॉट टाइम्स आई। आपने एलएचएस से शुरू किया था, इंटीग्रल बी डॉट डी एल से शुरू किया था, इंटीग्रल बी डॉट डी एल इज इक्वल टू, क्या रिजल्ट मिला आपको, इक्वल टू म्यू नॉट टाइम्स आई। बट दिस इज एम्पियर्स सर्क्यूटल लॉ। ना इससे एडवांटेज देखिए क्या, एक सोलेनॉइड की वजह से आप फील्ड निकाल सकते हो। एक करंट कैरिंग सोलेनॉइड आपके पास है तो फील्ड इनसाइड, मैग्नेटिक फील्ड इनसाइड अ सोलेनॉइड, ये आप निकाल सकते हो यूजिंग एम्पियर सर्किट लॉ। अगर आप यूज करोगे तो यू विल गेट B इज इक्वल टू म्यू नॉट एन आई। ये आपको फील्ड मिलेगा एक सोलेनॉइड के अंदर, वेयर N इज द नंबर ऑफ टर्न्स पर यूनिट लेंथ और I आपका करंट होगा। टोरॉइड की वजह से भी आप फील्ड निकाल सकते हो यूजिंग एम्पियर सर्किट लॉ, वो भी रिजल्ट ध्यान रखना यही आएगा, B इज इक्वल टू म्यू नॉट एन आई। इसके बेस के ऊपर आप क्वेश्चंस देखोगे मॉड्यूल के अंदर।